Friends, today we will extend the existing lecture on shear center to do couple of more numerical examples and also solve a problem where the section is not symmetric about any one of the axes. So, this lecture is lecture 28, Shear Center 3 in module 2 titled Advanced Structural Analysis under the NPTEL course of Offshore Structures under Special Loads, including fire resistant design. We already said that shear center will be located on the axis of symmetry. If the section has at least one axis of symmetry, shear center will lie on that axis. If the vertical load is applied through this point, the section will not undergo twisting or torsion. So, it is very vital for thin walled sections which are very common in offshore structures. In the last lecture we picked up an example. I will reiterate that example slightly and extend the discussion further in this lecture. We picked up segment of a curve extending for an angle 2 alpha with radius r and section thickness be t, this being the axis of symmetry. Shear center lies on this axis C, where the force applied through this will not cause any twisting, and the distance of this point from the center is the offset of the shear center, which we call as E, and we already derived that E is given by 2 R4 T by I sin alpha minus alpha cos alpha, where to the vertical this angle is beta. Now, let us discuss how to estimate the moment of inertia or the second moment of area of this section or this segment about the axis of symmetry. So, to find the moment of inertia I about the axis of symmetry. We know that I conventionally is given by this equation, we will cut a strip of segmental angle d theta at an angle theta from the vertical. So, now I can say integrate this r cos theta will be the distance, second moment of area, t d theta will be the area of the strip, and let this vary from beta to pi minus beta, because this angle is beta. So, which gives me, and the distance is r. So, r cube t beta 2 pi minus beta cos square theta d theta. So, we know that cos 2 theta is 2 cos square theta minus 1, therefore, cos square theta is actually equal to 1 plus cos 2 theta by 2. So, in the previous equation of cos square theta, we will substitute this as follows. So, r cube t by 2 integral beta to pi minus beta 1 plus cos 2 theta d theta, which simply says, now using the symmetry of the integral, we can now say beta to pi by 2 of twice the integral, where there are two strips about the axis of symmetry. So, now I can say r cube t theta plus sin 2 theta by 2 varying from beta to pi minus 2. If you look at the figure, one can write that pi minus 2 pi by 2 minus beta will be actually equal to alpha. This angle is beta, so pi 2 minus beta will be actually equal to alpha. So, since pi by 2 minus beta is alpha, using this relationship, we can now say I is r cube t. We earlier had theta plus sin 2 theta by 2 varying from beta to pi minus 2. We will say r cube t pi by 2 minus beta, that is upper and lower limits, plus sin 2 pi by 2 to minus sin 2 beta by 2, which can be r cube t pi by 2 minus beta minus. So, this term goes away, minus half sin, again beta can be expressed as twice of pi by 2 minus alpha, which can be r cube t pi by 2 minus alpha, beta is actually alpha, minus half so this term can be expressed as sin 2 alpha. So, that can be said as twice sin alpha cos alpha, which can be r cube t alpha minus sin alpha cos alpha, that is going to be I. Therefore, E is actually equal to 2 r 4 t by I sin alpha minus cos alpha. Now, substituting for I, we get E now equals 2 r sin alpha minus, oh there is an alpha here, there is an alpha here, alpha cos alpha by alpha minus sin alpha cos alpha, that is my E. So, E is 2 r sin alpha minus alpha cos alpha by alpha minus sin alpha cos alpha. So, that is the distance of shear center for this figure from the axis of symmetry from the center to the point which is E. Force angle extends 2 alpha at the center. So, we will take up now one more example. I think example 6 with symmetric sections. We will have a section like this. So, I have a section like this. The dimensions of the sections are, let us say this is T and from this point this distance is B to the center and this of course remains the axis of symmetry of the section. Therefore, shear center will lie on this line. This is O. Let us say the center of this is R. The section has uniform thickness T and this distance is B 1. Of course, this is also B 1. If you look at the shear flow diagram, we say this is V 1, we say this is V 2 and this becomes V 3 and this is V 4 and this is V 5. Let us say the shear center is located somewhere here. This is my shear center and I call this distance from the center as E. Now, we know from symmetry V 1 is equals V 5 and V 2 equals V 4. Let us find V 1. To do V 1, we will take a section of thickness dz whose dimension is z. So, V 1 will be integral 0 to B 1 V by I t A y bar d A. In this case, A is going to be t into z. Therefore, d A is t d z, and y bar, the distance of the fiber from the axis of symmetry. Actually, this distance, I am looking at this distance, this is from here to here, that is y bar for this case, which is going to be, let us say, r plus B 1 minus z by 2. Therefore, V 1 integral 0 B 1 V by I t t z r plus B 1 minus z by 2 t z, which gives me V t by I integral r plus B 1 minus z by 2 of z d z, which gives me V t by I r B 1 square by 2 plus B 1 cube by 2 minus B 1 cube by 6, which will tell me V 1 as V t by I or B 1 square by 2 plus B 1 cube by 3, equation number 1. Let us say I want to find V 2. So, I take a section at a distance x from here I want to find now the second moment of area of this whole strip about this point. So, V 2 is now equal to integral 0 to b, because that is the limit of this section 0 to b, V by I t uniform thickness A y bar d A. A is T x, d A is T d x. That is for the strip. Now, for the external arm, A y bar can be straight away B 1 into T, that is for this arm. Let us say I call this arm as 1. For arm 1, B 1 into T R plus B 1 by 2 is the y bar. Okay. So, now A y bar of piece 2, I call this as piece 2, will be T x into R. So, now let us find V 2, 0 to b, P by I t, B 1 t R plus B 1 by 2 plus T x into R of T d x. which tells me V t by I B 1 B r plus B 1 square by 2 plus B square r by 2. That is for V 2, equation number 2. Now, we want to find for the semicircular portion shear stress at any angle theta from the vertical. Is given by, let us draw the figure. Let us say you want to take say this angle, I say is theta, and of course, this small angle is d theta. Tau is given by V by I t integral y dA plus piece 1 plus piece 2, which will be V by I t r cos theta t into r d theta, that is for the semicircular strip, plus B 1 into t, that is piece 1 r plus B 1 by 2 plus B into t into r, which can be now said as V by I integral r square cos theta d theta plus B 1 r plus B 1 by 2 plus B r, which will be V by I r square sin theta plus B 1 of r plus B 1 by 2 plus B of r. That is my thought. So, the elemental shear force dV is given by dV is tau dA, which is V t r by I r square sin theta plus B 1 of r plus B 1 by 2 plus B r d theta. Now, we want to take moment of this force. So, moment of this shear force about center O is given by, we are taking moment about this point, center O is given by dm is equal to tau r dA, because that is the distance, is now going to be V t r square by I r square sin theta plus B 1 of r plus B 1 by 2 plus B r d theta. Now, the total moment of the semicircular portion will give me m as v r square t by I integral 0 to pi r square sin theta plus b 1 or b 1 by 2 plus b r of d theta, which gives me v r square t by I r square minus cos theta plus b 1 of r plus b 1 by 2 plus b r of theta varying 0 to pi. By substituting the upper and lower limits, we will get r square minus cos pi plus cos 0 plus b 1 of r plus b 1 by 2 plus b r of pi, which leads to v r square t by I r square 1 plus 1 plus pi times of b 1 r plus b 1 by 2 plus b r. Therefore, m will be v r square t by I 2 r square plus pi times of b 1 r plus b 1 by 2 plus b r. Now, taking moment of all these forces about m, about the shear center, or let us say about not the shear center, let us take moment about the point O. We know, look at this figure, the force V is going to act here and this is the distance E. So, it is going to be V into E, which is this m plus V 1 and the distance is B, is it not? But that is anticlockwise. Similarly, for V 2 the distance is R. Okay. So, m plus V 2 into R 2, because V 2 and V 4 are symmetrical. So, 2 minus 2 V 1 into R. So, E is now going to be m by V plus 2 V 2 R by V minus 2 V 1 R by V. So, interestingly, we have equations for V 1, V 2 and m, we can find E very easily. Now, the moment of inertia of the entire section about the axis of symmetry is given by I is going to be, I would request you to do it from the first principles and understand how this can be arrived, 3 pi plus 12 times of B plus B 1 by R plus 4 times of B 1 by R the whole square into 3 plus B 1 by R. So, that is my moment of inertia and this is my distance of shear center. So, friends, we are able to derive the distance of shear center or locate the point of shear center from the CG of a given section which has at least one axis of symmetry. We will take up one more example. This section has one axis of symmetry let us mark the dimensions of the section. Say this distance is B1 and this distance is B and this is also B and this is also B1. The section has uniform thickness which is T. So, let us say my load is going to act here and let us mark the shear center distance from this point as E. Let us mark the shear flow. So, the shear flow, this is going to be V1, this is going to be V2, V3 and V4. So, by symmetry we know V1 is equal to V4 and V2 is equal to V3. I want to find V1, I will take a section, let us say this is my section what I am cutting and this distance from here is Z, okay, and this thickness is dz. So, integral 0 to B1 V by I t A y bar dA. So, A is T z, dA is T t z, y bar is this center from the symmetry, okay, which is going to be okay, this angle is 45 degrees. So, B sin 45 minus B1 sin 45. So, B sin 45 will be this vertical distance, okay, this distance, and B1 will be subtractant of that plus Z by 2 sin 45 will give me y bar, which is B minus B1 plus Z by 2 of 1 by root 2. So, therefore, V1 is 0 to B1 V by I t T z, again T z B minus B1 plus Z by 2 1 by root 2, which will be V t by root 2 I B B1 square by 2 minus B1 cube by 2 plus B1 cube by 6, which tells me V 1 is V t by root 2 I B 1 square by 2 minus B 1 cube by 3 which can be simplified as V t B 1 square by root 2 I B by 2 minus B 1 by 3, that is my V 1. One can get in the similar fashion V 2. If you look at the expression for V 1, it is V t B 1 square by root 2 I B 2 by B 1 by 3, where I is the moment of inertia of the complete section, is it not, with respect to axis of symmetry. Now, this member is inclined and my axis of symmetry is here. I need to find the moment of inertia of this section of this piece with respect to this place. So, it is slightly tricky. I leave this as an homework to you for a day. Do this, we will try to find this in the next lecture and then extend this principle for sections with no axis of symmetry as well. Thank you very much.